Thank you very much, Christophe. Good morning, everybody. We know that it's not too hot this morning, so I hope everybody will be very concentrated on the topic. So my goal this morning during this first part, and there will be a second part given by Olivier after, is to give some basics about the main ideas and concepts of transfer learning with a focus on domain adaptation, with the main ideas and main algorithms, some theoretical justifications, but not that much. Just have to prepare to have a good overview of the domain of the main principles. So you already had some classes yesterday about deep learning stuff and machine learning for medical imaging, for example. And so ultimate goal of AI will be to have models that will be able to learn from the world, from tasks, and to build systems that are able to perform automatically some task. Actually, it's not already feasible, and what we are doing at the moment is to define some predefined tasks. Some basic tasks like old ones now to identify some digits, and then models have been improved to classify spams, to do some web search, or to do image segmentation. So what we try to do is to identify a task that the system is able to address by specifying some data set with some data that characterizes the task to achieve. And if we have enough data for some task, models are able to achieve some near human performance. It's also the case, for example, in medical imaging for some task. Good. But the problem is that to achieve very important performance, you need to have lots of labeled data. Okay. And it's not always possible because acquiring lots of labeled data is costly because you need to have this data, which is not always obvious to acquire, in particular in biology or in physics. So you need to have people who annotate this data. And then you may have some biases that depend on the way data have been acquired. Also, some data may evolve with time. So what you learned at some point might not be true later on. And also, there are too many tasks to address, and it's not be feasible that everybody can, lots of people could label sufficiently large amount of data. And this is where transfer learning comes. The idea is to try to build systems that will be able to adapt to new domains, to new tasks, by just refining some models or just aligning some statistics between data sets. And this will be the goal of my presentation this morning. So the general definition, high-level definition, will be to design systems that is able to adapt some knowledge and some skill to other tasks or domains. Okay. Original motivation for transfer learning methods is the following. You might have lots of labeled images that you have acquired from, let's say, labeled corpus, so a web corpus, like there is an image or there is no image. And now if you have some videos, you extract images from the video, if you want to address the same task, detect if there is a person in the image or not, since the resolution of the images, the colors are different, the system might not be able to detect correctly the concept and need to adapt the model to the data or to the setting of the new problem. So what are the differences? You might have cases where you have lots of very nice images with white background, but in practice, in the wild, the light might be darker, the cats could be in very wide environments. If you think to autonomous vehicles, you can learn from very neat images, but in practice, it can happen that there is some snow, there is some rain, and so the model has not been prepared to address with these conditions. Or in medical imaging, for example, you can have some images that are acquired from a given scanner with some given image quality. And if you move to another hospital, there is another scanner with other types of images, and so the model might not be prepared to address these two images, and we need to adapt. Right. So transfer learning is really the notion of adapting, transferring the knowledge that has been learned from a model to another task or domain. Domain adaptation is something where this is a subfield of transfer learning where we try to align distributions. So the idea is that you have a task like detecting some bikes and bags here. You learn from a well-knit data set. This data set has a particular distribution. And if you want to apply your model to another data set which share the same task, but the images are occurring in different environments, in the wild here, for example, the distribution of the images is different. And then this implies that the learning model to learn, which is here from the original source image, might not be correct for the new distribution. We need to adapt. What we try to do is to align two distributions in this field. Okay. And in domain adaptation is so a setting where what we assume in general is to have labels only from the source domain and very few or even no labels on the target domain. And then we need to try to adapt from the source to the target or from the training set to the test set. Right. What will be my outline this morning? The first thing, I will present some classic algorithms for transfer learning where we try to adapt a model that's been learned from a predefined task and then to adapt it to another task directly by making use of relevant features that have been learned before. And the second part, I will focus on domain adaptation, which tries to align distributions. And I will review different techniques that are among the state of the art. Okay, let's start by transfer learning. So if I try to refine a bit the definition, the idea is that, okay, you have a source domain where you have learning tasks, and from this source domain, you have lots of labeled data. And you are able to learn a very good model on this domain, right? And then you want to apply this one on a new target domain, T, where we have less labeled data or less data. So you can imagine that these are the medical imaging problem with a given imaging from a given scanner, and this is another medical imaging problem of the same task, the same prediction of tumor predictions, for example, but the images come from another scanner, which is different, with different properties. And the idea is to find a function or model, if we prefer, that will make use of the knowledge learned from the task source to adapt it to the target task, right? What are the usual settings that people try to address in transfer learning? First, you may have source and target samples of the two tasks, but depending on the setup, you can have labeled data in the source, not in the target. You can have labeled data in the source, very small labeled data in the target, or even no target sample, only labeled source samples, for example. And we'll see these settings along the presentation. If you have some labeled data in source, in general, you have more labeled source data than target labeled data. And you can also have some cases where you have the model learned on source, not the source sample, and you try to adapt to target sample directly. And also there are settings that I will not cover here where you have multiple tasks in the source, where you have data. You try to leverage some common properties between the tasks to learn a more robust model that will achieve all these tasks plus new incoming tasks, which is called multi-source or multitask learning. Okay. What's the idea of basic transfer learning approach is fine-tuning. What's the idea? The idea is that if you have a domain where you have lots of data, lots of labeled data, you try to learn a possibly big model from this data. Let's say a CNN-based model if you have images. Okay. And the idea, if you remember maybe the presentation you had yesterday, I think yesterday morning with Christophe, when you have these deep learning models, you learn some different level of features. And in the beginning of the model, you learn low-level features that could be general enough to be adapted to many tasks. And in the near decision layers, you have more specific features to the task. And the idea is that once you learned a model with big data sets, the features that you learn from the very first levels, okay, the low-level features, can be reused for other tasks because they are general enough. And so the idea will be only to specialize the specific features to the new task. And this is the goal of fine-tuning, to adapt only some specific features to the task. So the idea is you learn a model potentially big on lots of labeled data, millions of images. Then you freeze some layers that you think are general enough, shared, features that could be shared from all the tasks. And then you take the labeled sample from your target task, for example, doing some, producing some X-ray images, and you try to learn to refine the parameters of the last layers that are specific to the task. And you adapt the classification clearly here. Okay. But what is interesting here is that you don't have that, you have less parameters to train because you freeze a part of the network. And so if you have less data, it becomes tractable to learn to adapt these features here. Of course, the trade-off will be to select the number of layers you freeze that depend on the relatedness between the tasks. If the two tasks are very close, you can expect that only have to fine-tune the last layers. If the tasks might be more different, you might need to learn features from earlier layers. Can we justify this approach? Actually, there are some theoretical frameworks that justify that if you do this, you can have some guarantees on the model you learn. And for example, this result here defines the error that you make on the F part, which is the frozen part, and GT is the layer that you fine-tune on the task. And some results say that if what you can do is you can control this error by the error that you make on the source domain with the source model, plus complexity of the hypothesis space. The more complex your network is, the highest is the complexity, and also the complexity of the small function that you have here. And the message is that if this task is not too different from the target task, and if the complexity of models are relatively small with respect to the number of data you have, you can expect to reduce the target error by minimizing this kind of model. So it depends, of course, on the relatedness between tasks and the complexity of the models. Something which may be easier to get is if you imagine that you can change all the features from the source domain, so the source model. And what you try to do is, okay, let's take a new target sample. Let's try to learn a model that minimizes the loss from the target sample so that you are not too close from the source model, but you can modify all the weights that you want. If you do this, it can be shown that the error that you will obtain on the target can be modified by the error you observed on the target learning sample, plus the performance of the source model of the target task. So say differently, if the source model is not too bad on the target task, then without too much data, you are able to control the error that you will make on the target task just by reusing the source model. So say differently, if you have a source model that is not too far from the expected target model, you can expect to adapt it, even if you do not much data. That's the message. Okay, and the justification depends on the size of the models, the relatedness between the tasks. And the bad case is if your model is too far, what the impact is that this will be very high, and so the only way to compensate this difference is to add more labeled data. Okay, so if you have, it's like you need to retrain from scratch your target model. So in this case, transfer will not work if the task relatedness is not too close. Okay. Maybe you don't have labeled data in source. Okay, you only have the source data. You have lots of images, but you don't have people who are able to labeled your data. But you can still have a model that tries to leverage some basic elements in the images. And one way to do that is to use a model that will pre-train on your sample. The idea is that you will try to regularize the model by trying to make close images that are related. One way to do this is to take an image, let's say a dog here, and do some augmentation. I don't know if you saw that yesterday, maybe not. So the idea is that you crop a part of the image, you change the color, you flip the image. You take one image and you change it a bit. So from one image, you obtain two related images. And you can do this for all the images. And what you can do then is try to learn a network such that for the two images that come from the same image, you try to move them closer. And if you take three images that come from different images, try to move them far away. That's the idea. So then what you can try to do is to make up these images, do the augmentation, you obtain some representation at some point. And then for the images that are similar, you try to move them closer in that space. For the images that are different, you try to move them away. Once you learn that, you keep this part, the encoder here, and then you freeze them. And what you can try to do is to add a new classifier after the features you learn here to make a prediction, or do the same principle as fine-tuning that we see before, refine the tuning of the last layer of this model to adapt to your new target task. Okay. So the idea, even if you do not have labeled data on source, you can try to have a model that will extract common features that can be transferred later on the target task. Okay. One word about data augmentation. I will not spend too much time, but there are lots of work that try to define good augmentations for your task. Could be basic ones like flipping the image, doing some rotations, doing some noise, but also more refined method that is adapted to the target task. And of course, if the transformations could also happen in the target task, it could be better because you prepare your model for the target task. Okay. Now we'll focus more on domain adaptation, where we try to align the distributions from source and target. So the setting here is that I will have some labels on the source data and very few or even no labels on target. Okay. Just set a setting that will allow me to just justify bits the algorithms later. In the classic machine learning framework, right? We assume that the data that we observe come from an unknown distribution, the source distribution here. And we observe a labeled source training set from this distribution. And our objective is to be able to learn a model H that has a very low risk or very small probability to commit an error. That's the idea. Okay. So here, basically, I count 1 if I commit an error and 0 if my classification is perfect. It's binary classification to simplify this code. And the thing is that we do not have access to this quantity because the distribution is unknown. So what we can do is to measure the error on a source sample and to optimize the model on the source sample. In domain adaptation, we have the target domain. Actually, we want to be good on this domain, not on the source only. So we also have the same assumption. We have an unknown distribution, but this time we observed an unlabeled target dataset. We don't have access to the label, right? But still, we want to be good on the target true risk, so the probability that we commit an error on the target. And we assume that there is an unknown label function that follows the marginal distribution of the labels according to the instance. And what we want to do is to learn a classifier that works well, so that approximates well the target function f. The problem is that if we apply the classic machine learning guarantees, what we know in the basic model is that the error on the source domain can be bounded by the error that we measure on the sample, plus a term that measures a complexity in a broad sense here over the learning set. Over the learning set. And the idea is that, okay, you try to optimize this model without, by controlling the complexity of the model. If you do that, you can control the target risk. But you want to be good on the target domain, and we don't have labels. So it's difficult to control what happens. So we'll see how we can have some framework that allows us to learn some models. One word about the different shifts that we can observe, because here in the mediation we assume that two distributions are different. So what are the possible shifts? I put the three main shifts, but actually it exists other settings here, but the three main setups are defined here. The first one is coverage shift, which is the simplest. The idea is that, oh, sorry, I have a typo here, is that the distribution of the unlabeled data is, sorry, the distribution of the source and target actually are different, but the task, the concept to be learned is the same, but the distribution of the task, so I should have a different here, is different. So the idea is that the source and target share the same concept, so the same task, but the distribution of data do not occur on the same place because we have a shift in the marginal distribution on the instance space. In the label shift, the idea is that the distribution of the labels is different, but the distribution of the instances given the label is the same, which is illustrated here. Okay, we don't have the same probability of having a positive here target on source, but the general distribution of the instances is the same. And the concept shift is that we have a concept that changes between the two tasks. So here we see that the concept to learn is here, and the concept to learn is here. So we have changed both in the, sorry, there are some typos here. It should be different here and different here. So this one is different. I have to correct my slides, sorry. Okay. So what are the main strategies? The idea will be that you can take the two distributions, source and target, and what you can try to do to align two distributions is to decrease the importance of the source that do not share the same support as the target, and increase the importance of the source data that lie in the support of the target distribution, which is called reweighting. You can also try to align the distribution in new latent space to move closer the source distribution to the target one here. And this can be done by different methods like iterative approaches or domain alignment that we will see later. Okay, so first example, the reweighting method. Reweighting methods means that we want to change the weight of the instances depending on the distributions. Recall that we want to be good on the target. So this is the target error here. And what we can try to do to make the link between the source domain is to introduce the source distribution. Okay. So very simply here. Then we can refine the expectation by summing over the instances and weighting the models by the probability of the target here. We realize the terms, and then I obtain an expression over the source domain and the ratio between the target and source. Then if I assume that I have coverage shift, so the probability to a label given an instance is the same across the two distributions, then using Bayes' rule, I can obtain this, and these two terms will cancel out, and then the error on the target becomes the expression over the source domain over the ratio of the weight of the source target over the source times the loss. Okay. So the idea will be, okay, in that case, let's try to learn the ratio dt over ds to adapt the source domain to the target one. Okay, so the idea will be to learn this weight here. And then once the weight has been learned, we try to learn from the source, the weighted source domain. So we make use of the weighted of the weights learned to learn a classifier only on the source domain, which corresponds to put more importance on the source data that are close to target data. And to do that, there are lots of strategies. The principle is that you define a way to measure the weight. So it could be a combination of functions. And then you try to minimize the divergence between the weighted source and the target. You can also assume that I make some assumptions on the ratio, like logistic regression here, and try to learn a model that will learn automatically the weights by solving a regression problem. Or you could also change the divergence, like the maximum discrepancy here, which measures the difference of two distributions according to a kernel here, and try to learn a weight that minimizes this divergence. Okay, so the idea is take a divergence and try to learn a weight that minimizes the divergence. Also, another idea is that you can learn a neural network, W here, is a neural network, and you try to learn a neural network that will reweight the target data automatically to make source and target closer. And you can do this in a feature space, like the space that is provided by a neural network. Okay. So here, in this case, what we try to do is to learn the weighting scheme that allows the source to be close to the target. Bad news is that even if you have coverage shift, which would appear as a simple case, actually we might have some, it's an NP-hard problem actually to find a good classifier in the coverage shift problem. So we cannot expect that this problem is simple. And of course, coverage shift assumption is not always true. And the bad thing is that you might have a source domain like this and a target domain where the positive data correspond exactly to the opposite of the negative data of the source domain. And if this happens, you cannot expect to learn anything because, of course, you will not learn the correct concept. Okay? So domain adaptation is hard by nature. Sometimes you can learn a good classifier, but you might need to have lots of data or to introduce the good biases to find the correct model. And in some cases, if some simple assumptions like coverage shift do not work, then you might not be able to learn the correct concept without additional information. Okay. So when does it work? There is a classic framework that has been proposed by Benevin et al. In 2007, saying that actually what you can do is that the target error can be bounded by the source error plus a divergence between the two distributions plus a capacity term. This result is not difficult to show. And the idea is that the source error is exactly what you optimize with supervised machine learning. And divergence is the thing that you have to care about to try to move closer to two distributions. And the third term measures the readiness between two tasks, and you cannot really act on this model. Basically, this model tries to model the fact that if you have two tasks that are related, like you know how to drive a car, then you can drive a van. But if you know how to drive a car, you may not expect to pilot a rocket or to do some vehicle image classification. Okay, that's not basic, but that's what we try to do here. In practice, this lambda, I mean, there are different ways, but the basic one is to say, okay, you can adapt if there is a good classifier that is correct for the two tasks, two domains. If you have this, then the lambda term will be small and you can expect to adapt. You can refine this, but the idea is that this is a strong assumption that to ensure that the adaptation is true. Okay. And then the question is, okay, what we do, we assume that this is small, and then what we try to do is to work on the two terms here. One point is, which divergence can we choose? And there is one divergence called the H divergence, which in short tells you how far two domains are close. And if you go beside the formulas, the idea is that if I have my source domain here, I target domain here, if I can separate, if I can a classifier of my family classifiers can separate two domains, this means that they are very different. Okay, so divergence is high. If I cannot find a classifier that separates the two domains, then my two domains are close, and it's better to adapt. Okay, so divergences will be small. And so the idea will be to make use of a third divergence, and if we use this one, we can have a bounds like this, like the target error bounded by the empirical measure on source, plus the empirical measures on the divergence that you measure on the data sets, plus some complexity terms that are classic in machine learning. This is true for many divergences, and you can choose the one that you like for any reason, and you can adapt these results to other divergences. I skip this. So what's the principle? The idea is to try to learn a classifier H that minimizes joint error on the source domain error plus the divergence. Okay, that's the basic thing. You try to move them in a possibly joint latent space. However, this is difficult to optimize sometimes because you might have some loss information due to the suspect positions, and you might need to help you to have some additional target labels, data augmentation to robustify your model. But the principle is, okay, let's try to minimize the error while reducing the divergence between the two domains. And so to do that, there are lots of a family called subspace alignments, where what you can try to do is to align the two domains. So one very basic algorithm that I present, because actually it was provided here, is to align the two models by doing a subspace alignment. So it's very basic. You take the source domain, you apply PCA, you take the first D eigenvectors, you do the same for the target domain. You run projection operator that aligns the two domains, and then you project your source to the target. And then you learn a classifier from the projected source. So it's very simple. It's still unsupervised, but of course, this has the counterpart of unsupervised. It's not very accurate because you don't have labels. But it's a very simple way to align models. Now, if you want to do something a bit more controlled, you have optimal transport. So optimal transport, if you know this is a method that allows you to align distributions. Okay, and basically, what you're trying to do is to find a push-forward function that will transport the source distribution to the target one, according to a cost of function that you define. And so the idea is that you take the source data, you have the target data, you compute optimal transport path between source and target. And then this allows you to know exactly what to transport the source data to be close to the target. And then you learn the model in the projected space. So this works like this. You take your source data, you compute the optimal transport path, you move the source data to closer to the target ones, and then you learn the classifier in that space. And it's a very popular method that works pretty well, which allows to have some theoretical guarantees. Also, you can complete the models with iterative approaches. The idea will be to try to use some pseudo labels in the target domain. So here's an illustration. Imagine that I have my source, red labeled source and target in blue. What I can do first is to learn a model only from the labeled source data in red. Then try to label some target domains according to this classifier. And what I do, I keep the target data that are sensible for my classifiers. I remove the source data that are not very informative. Then I return the classifier and I iterate until I have labeled all my target data. And it's a way to integrate some pseudo labels from target in the source. Another very broad family is the free of deep learning methods. And what we try to do is to just do the same principle as I put it before, try to learn a model that will move closer to distributions while ensuring a good performance on source. And so there are lots of architectures that try to achieve the state of the art, actually. And one very key work is the paper on adversarial adaptation from Curien et al. That tries to do exactly what we saw before. We try to minimize the source error and divergence between two domains in the feature space defined by the deep learning model. And what we'll consider for the divergence, we'll consider the H divergence. And if you remember the divergence, it is high if we can separate the two domains, and it is small if we cannot separate the two domains. So the idea of this method will be exactly to do that, try to find a latent space where we cannot separate the domains while ensuring a good error on source. And for this purpose, the idea is that you have an architecture. Okay? So on the top, this is architecture for classifying your labeled task. Okay. And at some point, to control the feature space here, you have another subnetwork that is called a domain classifier that will try to check if we can distinguish the two domains from this feature space here. So the idea will be to check here, can we separate the source from target? So we define a new task, source is positive, target is negative, and we check if we're able to separate these two domains. If it's the case, we penalize the domain, so we try to maximize the error of identifying the two domains, while ensuring that the features are good enough to classify correctly the labels from the source task. Okay? It's a joint, it's an adversarial error problem, min-max problem. We try to find the weights here that minimize the error on the source task, and we try to maximize the error of identifying correctly the two domains. And it's min-max problem that are sometimes difficult to optimize. But the very good point is that you try to do exactly what you want, control the source error and control the relatedness between the two domains. One very quick word about validation. Hyperparameter validation in domain adaptation is actually a very hard task if you do not have target labels. So sometimes some people keep some more target labels to select the features. You can do some validation in that sense. I know only one heuristic that makes a bit sense is that what you can try to do is take your favorite domain adaptation method, do the adaptation, label your target sample, and try to move back to the source domain by doing the inverse of the adaptation from target to source. It's heuristic in the sense that you cannot prove that this will select the best models, but it's a heuristic way to control adaptation. One drawback is that it's very costly because you redo the adaptation process multiple times, and that's very costly. And now to finish, two very quick words on very active domains now. One is source-free domain adaptation. The idea is that sometimes you don't have the source sample before, you only have the model, okay? And the idea is that since you have the model, what you try to do is to adapt the model to the target data. And the idea is that you keep the source model, you take the target data, and then you try to control the weights of the source model by trying to decrease some entropy measures on the target data, include some diversity, only working on the source model. And the last field I would like to introduce is domain generalization. This time is that you want to prepare a model for the target task, but you don't have any target sample. So the idea is that you observe many source samples with some source datasets, and what you try to do is to prepare the training, to robustify the models, to be able to prepare it for checking from new target domains. And for that, what you try to do is to combine data augmentation, data generation, self-training, some pseudo learning, and to combine some models, some methods that will try to extract more complex transferable features that will be possibly seen in the target domain. So actually it's, probably the most interesting framework because you don't need to have the target data to learn model. You just need to prepare the source models to be transferable enough, but of course it's more difficult. Okay, some things that I've. Okay, I just finished. I didn't speak about teacher-students methods, meta-learning, generative, low-rank adaptation. So as you see here, there are lots of subfields that are very important in the domain. And so if you want to go into this domain, there are lots of areas. And my conclusion is that this transfer learning framework is very key for ability of machine learning methods. You may have very good operators of the task, but the understanding of these adaptation frameworks is still insufficient to completely justify the adaptation. In particular, measuring the amount of robustness, data augmentation, uncertainty, doing some parameter tuning, negative transfer. There are also some relationships with different flow matching methods that will be present this morning. If you want to a library, you can have a look to this library. And the next step to go beyond in transfer learning is to consider foundation models, where we try to have very robust models to favor adaptation, and this will be the objective of the next talk. Thank you very much.
Okay, thank you. Thank you, Amaury, for this overview. Do you have some questions? Yes. Yeah, thank you very much. You often use a complexity function. Can you detail it a little bit?
Yeah, so it's the case where you want to learn some theoretical models in machine learning. So you try to measure how a model or function is complex. So it could be basically the kind of size of the model. It could be so there are different settings. One, which is called the BC dimension, is how far the model is complex, how it can overfit a data set where you change the labels. So the more complex models, the more you can overfit. So if your complexity is large, you can overfit lots of data, and so you penalize the transfer in the sense, or the learning, because you need more data to ensure that you will not overfit. There are other strategies where you try to measure the complexity as a norm on the model complexity. So it could be the weights, could be the number of layers. And sometimes there are other complexities, like how far are you good from a prior model. You will measure complexity. If you know that your prior is interesting, how far are you good from that model. So it's interesting sometimes because if you measure the norms of a model, it could be very high. So your bounds is completely uninformative. So the one key point is to have theoretical boundaries that are informative in the sense that the bounds are not too large. And this is a difficult point because sometimes if you want to have something funny, you need to have lots of data. And we know that a very big deep learning model generalize even if they have billions of parameters. So the notion of complexity here is not well defined to always capture the notion of generalization.
Other questions? Yes.
So it's maybe a bit of a weird question. So when you try to do your adaptations, do you have an idea of how much it costs in terms of time or computing energy you need to put into it? And does that influence which approach you take? Like you have to do something, maybe you want it to be fast or to arrive quickly at an answer, or maybe it can be done better, but it costs too much. And how can you predict that?
Okay, so there are actually different answers to your question, if I understand correctly. It depends on your setting, because sometimes you want to be very fast at inference, and you have methods that are called test time adaptation. You are very fast to adapt to the data set you have to classify. It is very important. That's one way. Sometimes you want to be fast in the sense that you don't have that much data on your target task, and you want to adapt quickly to new tasks. So there is kind of few-shot learning where you have a method that tries to, let's say, initialize your model as well, and then you try to adapt quickly to new tasks with small number of samples. Here you need to have lots of tasks, so that's kind of way of quick. And then the question of time is also, for example, if you don't want to process all the source data, you only keep the source model, and then you work only from that model, which is a way to avoid to process the source data. If the model is too big, what you can try to do is to reduce this model by finding more compressed models, either by small architectures or to find a way to compress the weights in a subspace where you have less weights, and then work on this model, which will be smaller, and then more efficient in the sense of quicker to provide some answers.
Other questions? Okay, thank you very much again.